Okay, so this is going to be section 4.1, exponent rules, and we're going to be learning to solve a one-to-one equation, exponential equation. So the exponent rules we've talked about before in a previous lesson. So here's the rules as a recap. We'll go through them all again here real quick. So the exponent rules, you have a zero exponent. So any number to the zero power is a 1. Then you have the power rules. A number raised to a power raised to another power, you can multiply those exponents together. If I have a product inside parentheses with an exponent outside, then that exponent is on each of those base numbers inside. And this is just the division version of the same thing. So this exponent on the outside is actually on each base number on the inside. Then you have the product rule, where I'm multiplying numbers of the same base, then I add the exponents. The quotient rule is if I'm dividing numbers with the same base, I subtract the exponents. And another one we got to deal with also is the negative exponent rule. If I have a negative exponent, then that's really just a reciprocal action. It takes this quantity and flips it over the fraction line to get 1 over a to the positive n. So by flipping it over, the sign of the exponent changes to positive. And likewise, if I have a negative in the bottom of a fraction, I can bring it to the top of the fraction and change the sign of the exponent that way. So either one of those two options are available to you in the negative exponent. We're going to be using these rules to help us solve equations, exponential equations of a certain type. So we want to keep those in mind. And so then the next question that pops up is, what about fractional exponents? What about fractional exponents? Fractional exponents. We talked about this also in that previous video, but here it is again. What if I have a base number with a fraction in the exponent? Remember that this right here represents a root. So the bottom number becomes the index of a root. This is the nth root of a. Okay? So then we can use this concept right here and the power rule, like so. And then we can look at what does a to the n over m mean? Okay? And in that situation, n is the whole thing is an exponent. The bottom part of this exponent represents the root. So then this can be written as the nth root of a to the n, or you can write it as the nth root of a raised to the n. So you can write it in either one of those two fashions. And because the power raised to a power, you just multiply. Because what is this really? It's really a to the n to the 1 over m in exponent form. This right here represents that one. Okay? And if I switch those two things to the power raised to a power, you multiply them. That's how you get that right there. Okay? So we're going to use all these exponent rules that we just had to help us solve a new kind of equation, an exponential equation. And it is called, more specifically, a one-to-one exponential equation. We're going to learn to solve that. What is an exponential equation? It is an equation that has the x in an exponent, where your variable is in your exponent. That's what an exponential equation is. And here's the rule that we're going to be using. So, for base numbers cannot equal 1, if some number to a power equals the same number to a different power, supposedly, then I can simply just say the two exponents have to be equal. So this is the one-to-one rule for exponential equations. This would be an exponential equation because the variables are in the exponent. The b here is a base number. And so to use this rule, so this is a base number, to use this rule, what you need to accomplish is these base numbers must be the same number. And we're going to use exponent rules and such to help us make that happen. So that's our goal here. So that's the idea for this first section, using the exponent rules and to solve one-to-one equations. Since I've gone over exponent rules before, I'm going to show you an example now of what kind of equation you could be asked to solve. So here is 2 to the x over 3. And we're going to times that to 2 to the x over 2 power. And that has to equal 2 to the 5th power. So here's our equation. What does x have to equal to make this true? Okay. Well, let's run through some things. How do we think about this problem? So we need to use the exponent rules on the left to get a single 2 to some power. Okay, so we have multiple stuff over here. So we have a product rule going on. We need a single base number over here. So we're going to use the product rule. The product rule says if I multiply numbers with the same base, I add the exponents. So this whole thing can be rewritten as 2 to the x over 3 plus x over 2. And that's how you would use the exponent rules to help us simplify this problem to a point where we can solve it. Now we can see clearly that I have 2 to a power equals 2 to the power. So then I can use, because I have b to the x equals b to the y, see? B being the power of 2, the base 2. I can write this as x equals y. So I can write this as x over 3 plus x over 2 equals 5. And that gets those exponents down to into a normal equation that we can solve. So then, at this point, we're just solving a normal linear equation. Yes, it has fractions in it, but how do we get rid of fractions? We want to multiply by the least common denominator on both sides. And the denominator, least common denominator, would be 6. So we're going to put this side and that side in parentheses. We're going to multiply both sides by 6. 6 divided by 3 is 2, so this is a 2x. 6 divided by 2 is 3, so this is a 3x. And 5 times 6 is 30. Combine like terms. Divide by the 5 on both sides, and you get x equals 6. And we're going to learn to check our solutions also. You want to make sure that you do have indeed the right answer. You didn't make an error in here somewhere. So you take this number and you plug it up in here and see if it actually does work. 6 divided by 3 is 2. 6 divided by 2 is 3. And then we add the exponents. So 2 plus 3 is 5. And sure enough, it does work. So this is the kind of problem we're going to be doing. Now, you're going to come across problems where the base numbers are not so nicely put together. So to do that, we're going to need help changing bases. So to help in changing bases, what do we need? We need to learn some perfect powers. We need to learn some basic ones. What am I talking about here? I'm going to lay it out to you in the little table format instead of listing them all out. So we're going to look at, these are the numbers we're going to do powers on. I'm not going to do too many of them, but you can always extend this out if you want. So we're going to take this number and we're going to square it. So these are perfect squares. And then we're going to cube it for perfect cubes. And then we're going to go to the fourth power. And then we're going to do the fifth power. You can continue this up higher. Oh, can't see it. You can continue this higher if you need to. As you get better at this, you can extend higher and higher powers. But the higher you go in the power, you're not going to really deal with the need to memorize any of the ones beyond a certain point. The higher you go in the power, the lower you're going to go. First off, we already know what 1 is to every power. It's just 1 in all cases. So take all these up here and square them. Then I would have 4, 9, 16, 25, 36. This one you should continue at least all the way up to 12s. If you can go higher, that'd be great. There's a couple of ones that are used a lot that are squares. Learn those so that it helps you out. The cubes, 1 cubed is 1, 2 cubed is 8, 3 cubed, 27, 4 cubed, 81, and then 5 cubed is 125, and 6 cubed is 216. That pretty much ends it for sixes. The 216 is where you're going to see 216 quite often, so you want to know that that is 6 to the third power. Fourths, so we do this one all the way down to here. To the threes, we take this one all the way down, so this will be, this is not 81. I was going differently in my head. Sorry. That one's 64. This is 81. And then this down here would be 243. And then 4 to the fourth power. This will be the last one on this one. That's 256. That one's used a lot. And 5 to the fourth power is used a lot. And that's 625. So I would start with these numbers right here, get familiar with these. And that would help you tremendously in finding numbers that will help me match base numbers. Okay? So with that, I'm going to show you another example where we will use this to help us get the base numbers in the form so that they are the same base. So here in this example, I have 64 to the x plus 1 equals 4 to the x plus 7. So when you look at a problem like this, you always ask the question, can I make these numbers the same base? So usually it takes a bigger one and you want to make it into the smaller one. Sometimes they don't go directly, so you'll need to go to even a smaller one. For example, 4 can be written as 2 squared. So I can actually take 64 all the way down to 2s also. So we want the base numbers to be the same. So can I use perfect powers? Use the perfect powers to see if you can make that happen. So I know that 4 to the third power is 64. So I can take the 64 and write it as 4 to the third power. All I've changed was the 64. I didn't change the exponent up top. I didn't change this side at all because they're both powers of base 4s now. And now I have a power raised to a power. Using our exponent rules, okay. I lost it. There it is. So using our exponent rules, this becomes 4, and you can multiply it or you can just put it together. I'll just go ahead and multiply it. 3x plus 3. 3 times x, 3 times 1. And this is 4 to the x plus 7. Now I have the same base, so I use the 1-to-1 rule, and I get 3x plus 3 equals x plus 7. And that gets me to a linear equation that I can then solve. I'm going to add the opposite of the smallest to both sides, and I'm going to add the opposite of the constant to both sides at the same time, and I get 2x equals 4 So x equals 2. And then you can check your work to make sure that it is indeed true. And you should check it. Okay? And you can do that on a calculator. You can do that by hand. Just plug in the 2 up in here, 64 to the 3rd power, and then 4 to the 9 power, and make sure that they are the same value. They will be. Here's another one, a little bit more involved, but the same process. This time, I'm going to give it to you this way. Okay? And we want to solve this one. So now I have a fraction in here. Okay? Well, the first thing you want to do, even though it's a fraction, and they're both fractions, and they don't even have to both be fractions, that's fine. But the fraction is indicating to me that we might have an exponent, we might have something like this. So we might need to use a negative exponent right here. So that's what when I see those in this process, that's what I'm thinking. So I'm going to try and find a perfect power for both of those numbers. And in our little rules for this, we see that 6 is both a 36 and a 216. So this down here is 1 over 6 squared. And this one is 1 over 6 to the 3rd. Now I have the same base working here. It's still not the same base, but I'm getting closer. Now I'm going to use the negative exponent rule that takes this and brings it to the top. When it comes to the top, the exponent changes sign. When this one comes to the top, the exponent changes sign. Now I have a base number to a power, and the base numbers are the same. I have a power raised to a power, so I need to multiply. So you can actually, this time I'm not going to multiply it out in the exponent form. I'm just going to write it out as a multiplication. So this becomes 6 to the negative 2 times x minus 4. And this becomes a 6 to the negative 3 times x plus 1. So I can write it that way also. And then I can then use the 1-to-1 power rule that says this is negative 2 times x minus 4 equals negative 3 times x plus 1. And then I can just solve this linear equation. Now I can distribute this, and I get negative 2 plus negative 2x plus 8, negative 3x minus 3. Move the smallest one, so I'm going to add a 3x. I'm going to subtract an 8. And when I end up over here is I get x equals negative 11. And then you can check your answer to make sure that that is indeed true. So this is how you would go about these problems. Now, remember to check this. You can check this on the calculator, like I said. You can also use a graphing utility. Remember, if I have an equation, I taught you this, if I have an equation, I can graph the left side as one equation and the right side as another equation. And where they cross, I should have the x value of the solution. So if I do that, let's just check this out and see what happens. Let's see if I can get a screen here that's not so glary. So I type in this side over here, and so I'm going to get a parenthesis, and I put a fraction in there. I'll put 1 over 36, and then I'm going to raise it to, then up here I'm going to put x minus 4, and I can graph that. Now you may not be able to see anything right now, but I'll look at it later. Okay? And then I'm going to do the other one, and I'll type in the fraction 1 over 216. Okay, and I'm going to raise that one to the x plus 1. I'll graph that one. So somewhere they're going to cross. They're going to cross probably up here because we know the answer already is negative 11. So I'm going to change this thing. We're going to go way over here. So I got to change this window to see where it's at. And so it's going to be pretty high up there. And let's see, I'm going to do a zoom fit to see if I can find out where it's at. Okay, so you can see we're way over here. So I can also do this one. I'm on one of these things. I'm going to do a trace real quick. And then I'm just going to type in -11. Let's see what happens. And it's a little bit too high for the calculator. No, that didn't work as planned. But either way, you can just check this into by plugging it in and see where it goes from there.